This example is a two-variable product mix model, a classical linear programming model. This example is adapted from Ragsdale's book, Spreadsheet Modeling and Decision Analysis. Consider a hot tub producer named Blue Ridge. It produces two types of hot tubs, aqua spas and hydrolaxes. The basic information about these two products are summarized in this table. Each aqua spa needs 1 pump, 9 hours of labor, 12 feet of tubing, and yielding a profit of $350. Each hydrolax needs 1 pump, 6 hours of labor, and 16 feet of tubing, and yielding a profit of $300. In the next production planning period, let's say the next month, the company has 200 pumps, 1,566 hours of labor, and 2,880 feet of tubing available. The firm would like to find the product mix that maximizes the profit. The product mix is simply how many aqua spas and hydrolaxes to make and sell. Based on this example, we'll introduce a simple 5-step approach to formulating LP models. First, we need to understand the problem inside and out. Based on our understanding, we'll then identify the decision variables. In this example, it is pretty straightforward. There are two decision variables: number of aqua spas to produce and number of hydrolaxes to produce. Let's call the former x1 and the latter x2. Of course, feel free to choose your own name for each of the decision variables, such as x and y. Next, we need to state and formulate the objective function as a linear combination of the decision variables. In this case, the objective is pretty clear. We would like to maximize the total profit. The total profit can be written as a linear function of x1 and x2, that is 350 times x1 plus 300 times x2. Here, 350x1 is the profit the company can generate from making and selling aqua spas, and 300x2 is the profit that the company can get from making and selling hydrolaxes. To keep it simple, we assume that the Blue Ridge has sufficient demand so that all the hot tubs produced will be sold. Next, let's turn to the constraints. In step 4, we'll write down the constraints as linear combinations of the decision variables. In this example, we clearly have 3 resource constraints: pump constraint, labor constraint, and tubing or raw material constraint. Pump constraint essentially says that the number of pumps used next month cannot be more than the number of pumps available next month. Since each hot tub needs exactly 1 pump, the total number of pumps used next month or next production period is just 1 times x1 plus 1 times x2, which must be no more than 200. 200 is simply the number of pumps available next month. Similarly, for the labor constraint, the number of hours of labor needed next month cannot be more than the number of hours of labor available next month. The number of hours of labor needed next month is 9 times x1 plus 6 times x2, and the number of hours of labor available is 1,566 hours. So the labor constraint can be written as 9x1 plus 6x2 less than or equal to 1,566. For the tubing constraint, similarly, we have 12x1 plus 16x2 less than or equal to 2880. In step 5, we identify any upper or lower bounds on the decision variables. In our example, 2 non-negative constraints are implied. They are x1 greater than or equal to 0 and x2 greater than or equal to 0. It is meaningless to produce negative number of hot tubs. Of course, if you wish, you may combine step 4 and step 5 together and simply call it finding all the constraints. Now, let's put everything together and take a look at the very first LP model we have formulated. Here, I'd like to emphasize the importance of clearly defining the decision variables. Without clear definition of decision variables, the objective function and constraints are meaningless. People won't be able to understand what you are trying to do. Here, ST stands for subject to. It means that here are all the constraints. We'll make this an example of a good algebraic or mathematical linear programming model. When it is your turn to formulate an LP model, please remember to clearly define all the decision variables, to formulate the objective function, indicating whether it is a maximization or minimization problem, and to list all the constraints. In the next video, we'll solve this simple linear programming problem using a graphical approach.